Okay, welcome to today's lesson on Newton's laws. So we'll use the worksheet. Um, so in the mid-1600s, Isaac Newton proposed a few new things in life, working on the previous work of Galileo, who had stood on the shoulders of Copernicus. During a time period after the Reformation, not the Reformation, but as you have the Renaissance, then you've got people that are starting to study things in a different light than what they had over the last 1,000 years. And so Copernicus starting in the 1500s and Galileo in the 1500s to 1600s, and then Newton in the mid 1600s to 1700s started looking at things and actually trying to determine answers not just based on what church doctrine was saying. And so these laws that Newton postulates are really a restatement and with just a little bit more foundation than what Galileo had put together. So let's look at the first one. The first one says that an object at rest will stay at rest unless acted upon by an unbalanced force. Now, this is one that we believe. Okay, we love this one. This makes sense because if you've got a calculator on your desk, it won't move unless you push it. So we believe these things. But look at the second statement here. An object in motion will stay in motion unless acted upon by an unbalanced force. Now, in our experience, if we throw an object, let's say we throw a ball. Okay, we got a ball, we throw it. Gravity will pull it down. The force of gravity. Gravity will pull it down toward Earth. So the ball will fall down. And then it will roll and eventually stop. So for us, how can we say that an object in motion will stay in motion unless acted upon by an unbalanced force? Most students will say that gravity stopped the ball. Gravity doesn't stop anything. That's the first thing you should learn. Gravity is a force that's constantly being applied to objects around it. And it can't stop anything. Gravity can't stop the object. It's always going to continue trying to cause it to move. So it doesn't stop anything's motion. It may redirect it, like if you throw it up in the air, gravity will stop it from going up and then it will fall right back down. So if this person over here suddenly has a large hole appear underneath him, we all say, oh, well, yeah, he's going to fall because of gravity. So gravity can't be why the ball that's rolling along the ground stops. The reason the ball stops rolling is there is a friction force that opposes the motion. So in the air, we have air resistance, which is one form of friction. And then along the ground, we have what we would generally term, normal friction. Friction of the grass, gravel, sand, anything like that it hits. So we get that most things will stop, but we forget that this friction is being applied opposite of our current motion. So what Newton was seeing and what happened, and the reason he's able to see this at this time is Copernicus started the theory that the Earth was not the center of the universe with the sun and the stars and the moon rotating around it. Copernicus started saying, we got the sun in the center. And then Earth is just one thing out here that rotates around the sun. And then the moon does rotate around the Earth. And then Galileo proved it, and what they were able to do was, now that they had better telescopes, they could actually map these things a little bit better, and they could show it. And then what Newton was able to do was he invented a math called calculus. Okay, he and a man named Leibniz, I think that's his name, independently developed calculus. And how could two guys develop a whole new math going on? Well, it's what's happening in the world. People are starting to write and think outside the box, and we have better instruments to look at the moving bodies in the heavens, in space. And because of the way that they move, regular geometry and algebra don't account for their motion, and so they try to develop mathematical models that would state that. And this is where you could actually put this plate by looking at the motion of the planets and comets and stuff like that travel around the sun or out in space. We could see that these objects don't have a jet. We don't have the moon with a jet pack strapped to it, sending out these gusts over here so that it could circle the Earth. It's just the moon, just a big old rock, and it's going around Earth. And so how can it keep going around and around for thousands and thousands of years and yet not need any more energy like an engine or a propeller or a jetpack or something like that? Well, the reason is objects will stay in motion unless acted upon by an unbalanced force. So anything that is circling something else has to have this idea that gravity pulling it toward the larger object and vice versa. The object wants to go in a straight line, and the object is being changed because it's being turned by gravity. So we'll get into that a little bit more. But you can take a ball and put it on a string, twirl it around and around, and we'll do this later in our classes. And if you let go of the ball doesn't continue to go around and around on a string. It will go off in a straight line with the string hanging out behind it. So that's something we can see, that if you don't apply that force to the string to pull the ball back to you, it won't go around and around your hand. It will fly off in a mostly straight line. So an object at rest stays at rest. An object in motion stays in motion unless acted upon by an unbalanced force. This means that with no other force, the speed will be constant and it will go in the same direction. If no force is acting on it, the object will go at the same speed and in the same direction. Okay, law number 2 calculates the acceleration of an object when a known force is applied to a known mass. We've rearranged it to say F equals ma because we like to multiply instead of divide. But what he had seen, and Galileo had done these experiments, was that if a force is applied to cause an object to move, that the mass of the object, okay, the larger the mass, the less acceleration you get. The smaller the mass, the more acceleration you get. The larger the force, the more acceleration you get. The smaller the force, the less acceleration you get. So it says that it is proportional to the force. So if the force increases, acceleration increases. Force decreases, acceleration decreases. And then inversely proportional mass. So he's saying it's just the opposite with mass. If mass gets bigger, it's harder to move, so the acceleration is less. Common sense type things that we see every day. Law number 3. So we love law number 2. It's very specific. It's got math. And while every one of you hate math, it's the one we know what the answer is. It's easy. Do the math problem. You get the right answer. It's great. Law number 1, we like the first part. We don't really believe the second part, but it does exist. Look to the heavens and think about the fact that there's no jetpack or rocket on Earth, yet we still go around the sun forever and ever and ever. Law number 3, equal and opposite forces. So this is the fun one, and you see it, and it's one of those we also don't believe. So you've got a railing, and you're on roller skates. So a lot of us have gone to roller skating rinks, and you get the roller skates. If you push against the wall doesn't really move because it's so stable, but you roll back the other way. We know that. Well, in Newton's third law, it says whenever one object exerts a force on another object, the second exerts an equal and opposite force on the first. Or, for every action, there's an equal and opposite reaction. I can't push against the wall without the wall pushing back against me. You see this when you try to go open a door and someone on the other side opens it as you approach and you kind of lose your balance and stumble through. You're expecting resistance, it's not there. So you intuitively know that there's going to be resistance, and that resistance is a force. And when it isn't there, you're unbalanced. When you push against a wall and you're on roller skates and you go the opposite way, you're seeing this in effect. By pushing against the wall pushes back. And that results in the motion in the opposite direction of what I push. This is actually how all motion starts. If you're walking and you push off against, especially if you have a tile floor and there's any water along the floor, your foot may slip out. And the reason that is you're pushing backwards in order to go forwards. And so that's why your back foot, if your back foot slips, it slips backwards. If you step out and you are going to plant your heel or your foot on an area in the front that is slick, your front foot slips forward because you're actually pushing forward with your foot in order to control your motion. So walking is a tedious process of pushing backwards to go forward, but maintaining your speed by pushing forward with your front foot in order to control how fast you move forward. This is why if you're going down a very steep hill, it is very difficult to maintain your balance and run at the same time, because in trying to step forward, it's very hard to step forward and plant anything and control your forward speed because of the angle of the slope. And that's why a lot of times people will not fall because their back foot gives out, but they'll fall because their front foot gives out. So that's Newton's three laws. They're very simple and straightforward. We just have to apply it and some different things in our lives. So some definitions. A force is any action that can change or cause motion. It's measured in newtons. We often say it's any push or any pull. Okay, and you can only change the motion in the direction of the net force being applied. So we'll talk about net forces. Forces are vectors. That means they have a direction. And that's why we worked on vectors so much. Net force. Net force is when you add up forces. So let's look at this one. Let's take that negative out. Let's say 20 newtons left is applied and 10 newtons right is resisted. That means we have a net force of 10 newtons left. 20 is bigger than 10 by 10. So we have a net force of 10 acting on the box. And if there's no third force, like a friction force down here, then we would win. We see this in class. We went out and we played tug of war, so we could see that whoever pulls with the greatest force has a chance at moving somebody. But we also saw that application of the fact that mass, a very large person with a large mass, is hard to move. So even if they're not pulling much against you, it's hard to get that large person to move. Whereas if you have a very small mass, it's easy. If they're pulling as hard as they want to, they can't apply enough force to move the big guys. So we like to put that little bitty girl out there and have her pull hard and see that the big guy doesn't really have to resist much. But remember that the force that the big guy is applying to not move is the same as the force the little girl is applying to move. Net force. You take the two forces using our vector additions and you add them up. Inertia. Now here's a big one. Inertia is a property of an object that resists a change in motion. It is the mass of the object. That is important. Inertia is measured in mass. Inertia is not affected by the velocity of the object. We know that an object traveling very fast is much harder to stop than an object that's traveling slowly, but that is a different term. That is momentum. Or it could be kinetic energy, energy of motion. But it is not inertia. Inertia is all about the mass. A very large, heavy object is harder to move than a small object. A very large, heavy object moving is harder to slow down than a small object. And that gets back to the idea that F equals ma. So it gets back to F equals ma. A very large F or a small f, then F is going to equal a large mass and a small acceleration. And so since we have a large mass, let's do it this way, since we have a large mass and we have to slow it down, we're going to have a large force. Whereas with a small object, everything being the same, because we have a small mass and a small acceleration, then we're going to have a small force. So the size of the letter is supposed to help out. The fact that the mass is what's different in size. Both objects travel to the right at 10 meters per second. Much harder to slow down the large object than the small object. Again, that's one of those things we know. It's just applying it into what we're talking about here in our science terms. Balanced forces mean your net forces equal 0. Unbalanced force means net force is not 0. Remember Newton's first law, an object at rest will remain at rest An object in motion will remain in motion unless acted on by an outside unbalanced force. So if your forces are balanced, it will keep doing what it's already doing. That means there is no change to speed and no change to direction. It has to be moving at the same speed in a straight line. Balance forces being 0. Net force not equals 0. If net force is not equal to 0, we must have acceleration. We must have acceleration. That means there must be a change to the speed, or there must be a change to the direction. Remember that acceleration, I'll write it up here at the top, acceleration equals the change in velocity over time, and velocity is speed with a direction. So if your forces are balanced, there's no change to your motion. If your net force is unbalanced, then that means it's a positive or negative number, left or right, up or down, and that means we have to have a change in our motion, change in our speed or change in our direction. So that's the theory behind what we're going to be doing in Newton's laws. So good luck as we go through these processes. It's a very easy thing. It's very easy to see what's going on. We just have to apply the fact that objects on Earth are going to slow down because of friction. Air resistance, friction, when they come in contact with something, those will result in slowing down because of friction.